This afternoon, it's my pleasure to introduce our speaker today. Professor Bowie Ji is an associate professor of statistics here at Purdue University. She's been on campus since 2004, I believe. And even though she did receive her degrees from the University of Michigan, we still enjoy having her here on campus at Purdue. So I think that it's kind of unusual to think about statistics when you talk about cybersecurity, although math is at the heart of it. And what I really like about her topic, it's something that we're going to hear more and more of, is she's taken a game theory approach to looking at and machine learning. So she's combining two very hot topics into her security presentation today. So with that, I'll turn it over to Professor Ji.
Yeah, actually, thank you for a very nice introduction and the invitation for the talk. So the work I presented here is a summary of several papers I wrote with my student and collaborators from Dallas. So we all know there are malicious attacks, right? In cybersecurity, well, there are network intruders, and spam emails is another example. Spammers constantly rewrite the spam email, then spam filter, which serves as classifier, cannot label them correctly. And very recently, this received lots of visibility, rather because of deep learning. So deep learning-based systems are very sensitive to minor input perturbations. So one famous example is the stop sign example, right? They try to put on a few stickers on the stop sign, and then stop sign will be misclassified as speed limit sign. Well, that even has a different background color. Another example is rather physical, attack, or attacking physical layers. So it's called dolphin attack. Well, they design ultrasonic commands, which is inaudible to human. But these ultrasonic commands can control almost all the speech recognition system by targeting on the hardware. And it can even control the navigation system of a car. Adversarial machine learning is talking about handling data points that has unusual properties. So from cybersecurity and from computer vision, we actually see two classes of adversarial samples. One is adversarial samples that's very similar to the standard normal samples, but cannot be recognized. Another class is adversarial samples suddenly have very different properties. Say follow different distributions compared with the test sample. Then, standard machine learning techniques cannot handle these adversarial samples. Well, we need a whole new class of machine learning techniques that can deal with adversarial attacks properly. Somehow. Okay, so there's another topic is artificial intelligence. Artificial intelligence is rather broader. It's not limited with machine learning. But right now, artificial intelligence also is forward thinking, just try to improve the capacity, increase the accuracy, and it needs adversarial machine learning capacity. So it needs to be able to handle malicious instances and still act properly. And game theory actually offers a very useful tool to model the interaction between attackers and defenders. And here we assume a defender is a learning system. And we could have multiple adversaries. Well, my past work actually addressed supervised learning in an adversarial environment, unsupervised learning, and active learning algorithms facing active adversaries. And as for deep learning, we show, if we use randomized decision boundary for deep learning models, then we'll be able to break transferability of adversarial samples and classify the instances properly. So the first work, we use a sequential game, adversarial stackable game, to model the interaction. So in adversarial stackable game, one player will make the first move, and after observing the first player's action, the second player will choose its strategy. And in this sequential game, every player can have their own utility function. and they try to maximize their own payoff. So it's different from the zero-sum game. In zero-sum game, well, one player's gain is another player's loss. But in the sequential game, I often receive questions about, well, who should be the leader in the game? We have defender, we have multiple adversaries. Well, in the, when business school, their studies use stackable game, the conclusion is the leader has an advantage in the game. Say the largest company being the leader in the game, they set the price for a product, then they receive the largest profit. Here, well, in adversarial game, well, we'll compare two different scenarios, two different games. One is we like the defender to be the leader in the game, and all the adversaries become the follower. Then this is a one leader and follower game. Another scenario is we let the defender be the follower in the game, and the adversaries are the leaders. So all the adversaries, make their move. Then defender will choose a defensive strategy. Then this is a I'm leader, one follower game. Well, the game setup actually is a complex optimization problem. So we are searching for the equilibrium solutions in two different scenarios. The details in the preprint paper is currently under review. Well, in the game setup, well, we first need to define the strategies for each player. And defender's strategy is to draw a defensive wall around the center of the normal population. So the size of the defensive wall is controlled by a parameter between 0 and 1. Well, we can imagine this defensive wall is comparable to a confidence region we use to draw in a multivariate normal population. So the parameter alpha is comparable to a confidence level in the normal population. And attacker's strategy, attacker's strategy is to move the objects under their control toward the center of the normal population. And attacker's strategy is also controlled by a parameter between 0 and 1. 0 means, well, no movement, stay at the original position. Then 1 means move it, at the center of the normal. Then strategy space for both players, or all the players, are bounded between 0 and 1. And next in the game, we need to define each player's payoff. Attacker's payoff are the expected value of the utilities generated by adversarial samples that successfully evade detection. And defender's payoff is -1 times misclassification cost. So to solve for the equilibrium, well, in a multiple follower, multiple leader game, it's a very complex optimization problem, solving for the saddle point. And in our setup, because, well, all the strategy space is bounded, so we actually do an exhaustive search. And, well, here are the two equilibrium strategies. On the left, that's where defender is the leader in the game. And defender's equilibrium strategy is a small red circle around the blue points. And attacker's equilibrium strategy are the black points that's on the boundary of the normal population. So on this plot, green points are the original attack objects. Black points are the new attack objects. And blue points are the normal points. Normal population position, we assume that doesn't change. And the right panel shows the equilibrium strategy when defender is the follower in the game. Well, the red circle is larger, it's a more relaxed strategy, and we can see more blue points, more normal points are properly classified. And well, when defender is the follower in the game, we see the black points are not very aggressive. So they're away from even the boundary points of the normal population. So comparing these two game setup, we basically see when defender is the follower in the game, well, defender has an advantage in the adversarial environment. So when defender is the follower, defender has the advantage to observe all the adversary's moves. And when adversary is not aware of the existence of the defensive strategy, they make less aggressive attacks. And defender is able to draw a more relaxed decision boundary to have more normal points properly classified. And on the other hand, well, if defender is the leader, defender first needs to decide on the defensive strategy, say the spam filter. It needs to set a more conservative strategy, block out many normal points. And observing the existence of such a defensive strategy, adversaries, well, tends to launch more aggressive attacks. So this conclusion is very different from the business studies. Well, and next, well, we address adversarial learning in unsupervised environment. So we observe adversarial samples mostly from two different application domains. One is cybersecurity, another is computer vision. And adversarial samples in these two different, in cybersecurity and computer visions, have very different properties. Well, in cybersecurity, well, first of all, we may not have many labeled data points. When there's a new attack, say a new malware or a new, completely new attack, we may not have the luxury to label the new attack objects. Or we may have completely unlabeled data set, say for anomaly detection technique. Then we still need to be able to have a robust learning algorithm that can learn the adversary's behavior from large amount of unlabeled samples. And we notice adversarial samples in cybersecurity, they can certainly have very different distribution or very different property from the standard training samples. And to attack unsupervised learning technique or anomaly detection technique, well, adversaries just needs to fill in the gap, place a few objects between previously well-separated clusters. Then multiple separate clusters can be connected together into a large mixed cluster. And currently, well, the work on adversarial learning mostly focuses on classification tasks. So they assume there's a large number of labeled data points. In computer vision, this is easy. Images are free. But in cybersecurity, it may not be a realistic assumption. Oh, okay, let me. So our algorithm can achieve multiple objectives. So we first try to identify the subclusters, normal subcluster or abnormal subcluster inside large mixed clusters. And next, our algorithm will not label all the unlabeled data points. So this is different from semi-supervised learning. Well, in semi-supervised learning, it assumes there's a handful of labeled points and a large number of unlabeled points. Then it gradually tries to identify the most accurate classification boundary, which achieve the highest accuracy on all the unlabeled data points. And for our algorithm, well, we will preserve unlabeled regions between normal and abnormal subclusters. Those unlabeled regions is comparable to confidence regions. And compared with the classification boundary can be considered as a point estimate. So given very small number of labeled data points, well, this point estimate is not accurate, even through semi-supervised learning. And using, save the unlabeled confidence region and try to identify high confidence normal regions will be a more appropriate approach. And at the same time, we also identify outliers as potential anomalies. And our idea to identify the high confidence regions inside large mixed cluster, we can imagine is comparable to airport security. So in airport security, only a small number of passengers will go through the fast pre-check lane. Most of the passengers will go through the time-consuming security check. But so far for the past a number of years, all the passengers are normal passengers. So basically in adversarial learning, any objects outside of the high confidence region needs to go through second level screening. This will prevent adversarial samples to enter the high confidence region. So our algorithm actually have two, we need to take two parts of the data. On the plot, on the left panel, the orange points are the abnormal data points, blue points are the normal data points. So we see three clusters together, form one large mixed cluster. If we don't, have any additional information, just use a standard clustering algorithm. That's what a clustering algorithm will return: a large, mixed cluster, unlabeled mixed cluster. And for our algorithm, we assume there's a handful of labeled seeds, could be just 0.5% of the data set. Then, using the labeled seeds, we first compute the probability densities of the data point. So it's a grid-based algorithm. In grid-based algorithm, feature space are divided into spatial cells. Then it computes the density in the spatial cells. We'll use the labeled seeds to first compute the probability density in each spatial cells. Then the neighboring spatial cells with high density, high probability density will be grouped together. In the first pass, we'll form three types of small clusters. We'll have labeled normal subclusters, labeled abnormal subclusters, and unlabeled small clusters. Then in the second pass, we'll ignore the labeled seeds. Just run the grid-based algorithm again. It will return large clusters, large unlabeled clusters. Then we'll match the results from the first pass with the results from the second pass. We'll identify the position of the small clusters from the first pass. Match them into the large unlabeled cluster. Then the panel, in the middle panel, show the results from our AD class algorithm. So we identify orange points, blue points, three subclusters into this large cluster, and those purple points between orange and blue points, those are the unlabeled points. So they identify an unlabeled region, like a confidence region, between subclusters. And the position of the subclusters can be arbitrary in the large cluster, in the large mixed cluster. And the shape of this unlabeled confidence region can be quite flexible. And then we also have black points. Black points are identified as outliers, potential anomalies, no attack objects. The right panel is the results from a semi-supervised learning algorithm. Basically, we run different semi-supervised learning algorithms. They more or less give very similar results. So semi-supervised learning algorithm use the same labeled seeds, try to identify a classification boundary in the center. So around the center of the orange data points, then we can see it completely misclassified one normal subcluster, and also didn't get the structure of the three ABA structure. The results here is from one real data set. It's a network intrusion data set collected in 1999. And in this KDD cup data set, 40% network intrusion instances, around 60% are normal instances. And here, in one round, we keep 100 randomly sampled instances, keep their labels. Then basically 99.6% will be unlabeled data points. Then the data points in our high confidence regions, 90% of them are normal data points. So we compare with on average 60%. We do identify high confidence regions. And network intrusion data is highly mixed. So it's very difficult to identify intrusion data, intrusion instances from normal instances, which achieve good results in here. We are currently running on another larger cybersecurity data set with 110 dimensions, and we still have good results. So our algorithm scale up to high dimensional results as well. And as for the size of the defensive wall, well, the size of the defensive wall, that red circle, actually, in the middle panel, there's small blue circles. So blue circles are the defensive walls. They identify the high confidence normal regions. The size of the defensive wall is determined through that previous game theoretic study. So when defender is the follower, in general, the equilibrium strategy will recommend defensive wall size around 60%, between 60% to 80%. Not too conservative, not too relaxed. And in the KDD CAP data, we also recommend the same range, between 60 to 80%, to draw further defensive, high confidence region. Then another approach, utilizing a small number of labeled seeds, is active learning. So active learning algorithm will start from a very small number of training data points. Then it will sample the most influential data point. An oracle will provide a label for this influential data point. Then by gradually increasing the size of the training data, while active learning algorithm will achieve the same accuracy as a standard classifier, say a support vector machine or a logistic regression. But active learning, by sampling the more influential data point, to be labeled and including the training data, it uses a much smaller training data set compared with a standard classifier. But here in adversarial setting, we'll imagine the oracle that provide labels for the sample data point can be controlled by adversaries. So here we assume there could be three types of oracles. One is a genuine oracle. It just always provides correct labels. Another type is noisy oracle. So it will not purposely produce wrong labels. It just, by probability, will not get all the labels correct. For example, in crowdsourcing, while people just label instances very quickly, then there's an error rate. But it doesn't, purposely try to hurt the performance of the learning algorithm. The third type of the oracle is malicious oracle. Malicious oracle are controlled by the adversary. It will targetedly produce wrong labels. And hopefully, try to reduce the accuracy of the active learning algorithm as much as possible. I also skipped the actual algorithm. This paper is going to appear in a workshop in PAKDD conference in April. So the algorithm is iterative. So we try to estimate which oracle is genuine oracle, which is malicious oracle. Well, we first cluster data. Based on the data clustering results compared with the labels produced by the oracles, we estimate which ones are the genuine oracles. Then we'll use only the estimated genuine oracle to label the sample data point, increase the training data set by 1. So in this iterative process, we run it on the web spam data. And here, 60% of the instances are spam instances. And we compare our adversarial active learning technique with simple majority vote, with crowdsourcing technique, and also with standard active learning technique without malicious and weak oracles. Underlying classifier is support vector machine. So this is the typical results for active learning. As training size gradually increase, so we start from 20 labeled training data points, gradually increase to more than 100. So the top line, we are plotting the accuracy of the active learning algorithm. On both right and left panel, the top line, the most accurate technique is the standard active learning technique, where oracles always produce the wrong, correct labels. But that bold black line, that's the accuracy of our adversarial active learning algorithm. So on the right panel, we assume there are 30 oracles. 10 are genuine oracles, 10 are malicious oracles, 10 are weak oracles. Then after about 80 training samples, label training samples, we'll be able to estimate which are genuine oracles, and our accuracy, quickly match the accuracy of the standard active learning technique. But the difference between 4 algorithms, even between our technique and majority vote are not very significant on the right-hand side. So on the left-hand side, we look at a more extreme example. Out of 3 oracles, we assume only 5 are genuine oracles, 13 are malicious oracles, 12 are noisy oracles. So here we see a more a better comparison of 4 techniques. Well, our technique will be less accurate than the standard active learning technique, but majority vote is just like flipping coin, and crowdsourcing technique is less accurate. So that's the results in mostly unsupervised learning or weakly supervised learning scenario, when we basically applications targeted on cybersecurity datasets. Next, we'll look at supervised learning scenario. Supervised learning scenario assume large number of labeled training data points, but this is often the case in computer vision domain. And here we consider 2 techniques, rather 2 strategies to make machine learning technique or classifiers more robust against adversarial perturbation. One is to draw a conservative strategy. So both strategies are inspired by game theory. Well, in game theory, the equilibrium solution is a more conservative solution. Basically, we draw the decision boundary toward the center of the normal population. Then it's more difficult for the adversary to reach the boundary of the new conservative decision function. Then another strategy is to have randomized decision boundary. So if we randomize the decision boundary, then it's more difficult for adversaries to discover where is the decision boundary and to create adversarial samples. So the first technique here is adversarial support vector machine. Here we draw we take the conservative strategy. Support vector machine in general solves a convex optimization problem. So we define hinge laws, then try to solve for the decision boundary. Here, if we somehow incorporate support vector machine with game theory model, support vector machine is already optimization problem. Game theory is another optimization, problem. Then we are going to have a double loop of optimizations. So for adversarial support vector machine, we simplify the algorithm. We don't directly use game theory, but instead we try to model the attack and incorporate anticipated attack inside the risk minimization formulation, inside the loss function. The actual setup of the new loss function and the attack model in the paper is a KDD paper. So basically, we consider 2 possible attacks. One is free range attack. In free range attack, objects can be moved anywhere in the feature space. Another scenario is targeted attack. In targeted attack, adversarial objects must move toward a normal value, a normal object, randomly selected from normal population. Then, based on the attack model, we rewrite the loss function in the risk minimization problem and compute a different conservative support vector machine decision boundary. So this is a comparison of the standard support vector machine decision boundary and the more conservative decision boundary. So here, red points are the abnormal data points, green points are the normal populations. The dashed line is the standard decision boundary, basically achieves the best separation between 2 classes, and using kernel function could be a nonlinear decision boundary. But the black points are the actual attack data points. If we if in the risk minimization problem, we put in the correct put in the properly estimated attack model, then the blue line is the revised, more conservative decision boundary. It managed to block out most of the attack instances. But if in the risk minimization formulation, well, the anticipated attack strength doesn't match the actual attack, then, well, we'll see more, well, wrongly labeled normal objects, and more attack objects can, breach the boundary of the adversarial spot vector machine decision boundary. So we run large set of simulation. Basically, if we do not really observe the attack objects, well, the risk minimization problem better to predict the medium strength attack and draw a decision boundary, but not too conservative. So the next randomized decision boundary strategy, we apply it to deep neural network. So for deep neural network, this is why in the past couple of years, adversarial machine learning suddenly becomes a very popular topic. So images, well, with very minor perturbation, can easily be misclassified by deep neural network model. So the left is a handwritten tree that's correctly labeled. And on the right-hand side, there's a misclassified tree. We see just a few pixels on tree is missing. Then it cannot be labeled correctly. So deep neural network become very popular classifier and eventually outperforms spot vector machine its on image classification tasks. In 2012, well, on ImageNet competition, deep neural network clearly outperforms spot vector machine. That's why deep neural network is used widely in computer vision and audio classification tasks. But it's also very vulnerable. It's less robust than spot vector machine. That's the current conclusion. And our results is try to improve the performance of neural network facing adversarial images. So there are many different attack algorithms designed to generate the perturbations, and then a new adversarial image. So famous example is Kalinin-Wagner's iterative L2 attack. There's also moment-based attack. Also attacks somehow try to estimate the randomization technique and recompute the gradients. But these are all gradient-based. Basically, they use objective function, try to define the minimal amount of perturbation added to an image, and compute the gradients to change the pixel values on the original test image and generate new adversarial images. So more or less all the attack algorithms follow the same gradient-based approach. And here, with the adversarial samples, there's one interesting phenomenon is observed. It's called transferability of adversarial samples. So people discovered, if one adversarial image is generated, to break one deep neural network model, then the same adversarial image will be misclassified by other neural network models with very different structure. Or it can even happen, across different model classes. It can even be misclassified by spot vector machine or just regression-based image classifier. And here we see, if we randomize the decision boundary of deep neural network, we can successfully stop transferability of adversarial samples. So in a sense, make neural network more robust against attacks. So we actually consider two attack scenarios. In the weak attack scenario, we assume adversaries know only one neural network. Adversaries know the structure, the parameter value of one neural network. But we will train a number of neural networks by just using different random initial points in the training procedure. So neural network is very vulnerable even starting from the training process. If we change, the initial values, we end up with different enough neural networks, different enough models. So here we train 10 neural network models. basically, if you have a pool of 10 or 20 neural network models, then that's sufficient to randomize the same boundary. And the baseline deep neural network is a neural network that actually known to the adversary. So adversary know the structure, know the parameter values. Then adversarial images will be generated toward that baseline deep neural network. Then it has performance, accuracy 0% on the generated adversarial images. And here we also compare with a defense strategy. It's called ensemble adversarial model. So one major class of defense strategy is to retrain neural network using adversarial images. So it's called adversarially trained neural network. And we can train one, we can train ensemble. But it has also some problems. One is the adversarial images involved in the retraining procedure is overfitted. And once you retrain the model, it's a new model. Then new adversarial images can be generated toward the new model, the retrained model, and still, new model will have 0% accuracy. So for the weak attack scenario, we can have multiple defense strategies all achieve good performance. So first one, for every new test sample, we randomly choose one trained model from a pool, say 10 or 20 trained models, to classify that test image. On average, accuracy is 86%. This is average over 50 or 20 runs. Another one is simply use the majority vote of all the trained models, 10 or 20 of them. And because adversary knows only one model, the majority vote also achieves good accuracy, 99%. And third one, we randomize among the retrained models. So for every test image, we randomly pick one retrained model. Accuracy increased to 87%. The last strategy, in the weak attack scenario, basically every time for new test image, we randomly choose a model and inject random noises to the parameter value, to the parameters in the neural network. So we not only randomly select one model, we also randomize the parameter value. But under this stronger randomization strategy, the current accuracy is 77.9%. But later, we consider a second stronger attack scenario. We assume the adversaries know all the trained models, all the 10 trained neural network. Adversaries know 10 models structure parameter values. Then it can generate adversarial images attacking all 10 models. And with that strong attack, basically only the last strategy still works. So when we inject random noises to the trained model, we basically form random ensemble, and we still maintain the accuracy about 80%. So what we observe here is, basically there's a trade-off between accuracy and robustness. The simple majority vote is, has the smallest accuracy, 0%, in the strong attack scenario. But for the weak attack scenario, has the highest accuracy. And for the random ensemble, accuracy on the weak attack scenario is the lowest, but it will maintain this level of accuracy on the strong attacks. So this is another phenomenon observed recently, in robust machine learning. We probably need to have a systematic way to try to quantify the trade-off between robustness and accuracy. And for future results, how to build robust deep learning models, or in general, how to evaluate machine learning techniques' robustness against adversarial samples, it's still open research area. And another thing is, deep neural network is almost a black box, and we need to understand how deep neural network reaches conclusion. So, make the decision more explainable. Then, in time we should be able to further improve, the generalization area of deep neural network. So my related publications are on my website. Yeah, thank you. Yeah.
Are there any questions? Okay, if no questions, thank you very much.
Another point, this topic area is well funded, by different agencies. So I'm actively looking for students who want to work on this topic. So if you're interested, please talk to me.